Well, in the interest of time, I'll say a bit about the structure of Sean's dissertation. It has 3 parts, and the Mars part, which is what he worked on earlier, involved 4 different papers. Okay, he's getting his program up. Is people able to see that now? Marsscapes, Terrestrial?
Yes,
Yeah,
sir.
okay. So you've got connection, and Dr. Ferre will be joining us, I presume.
Turn the hell off, so it's not.
That was outside.
No,
The windows.
Yeah, projector.
Yeah, turn the projector off. There's a button for the projector. Yeah, there's a.
Yes. It's, yeah,
TV.
no, the other one.
The other projector. Yes.
Yeah, keep pressing in. Okay, there, double click it.
Oh,
So,
okay, we're set.
That was something.
oh. All right.
You can go to full screen if you want.
So Ty, you missed the adventure of the incredible breaking couplings. They walked in the door. Broke the screen. This thingy's on top of my. F5. Wonderful. Yes, folks. I used to work in the computer industry.
Slideshow.
I think you can go to full screen too.
Yeah, I can't.
If you go down all the way to the bottom, right next to the slider bar, to the left of the slider bar, hit that little screen thing. Oh, went away.
Wrong one.
There we go, down to the bottom. There's a little screen thing to the left of it, like this thing right here. On that thing.
There,
There it goes.
now you got full screen.
Yeah.
Wait.
Okay.
Okay. So, I think you all know me. If you don't, and you just popped in, you have quite an adventure here. John Wheelock, a PhD student here, also the Hat Creek hydrologist, Lassen National Forest in Northeast California. And we're up the bottom of the screen. It's kind of weird. Anyway, the slides are going to be okay. The slides are. The first thing I was going to say is just thank everyone for being here. Vic explained part of why it's such a monumental thing. The prognosis was that I was never supposed to walk on it again.
So they can hear you.
They cannot hear me. Oh boy.
They hear you have to like.
Okay.
Yeah.
Your, volume on
Yeah.
your, and then just point it towards Sean.
Okay. Now, can people hear?
Is that better?
That's much better. Thank you.
Better. So
I tend to mumble. So if I start mumbling and a far away speaker and can't hear me, please try to get my attention. Oh, it's Vic's camera too. Oh.
See, it's hot at the same time.
yep. We'll see you and we'll talk.
Okay. I look at this one, I click this one.
All right, thank you.
Thank you. Can you actually see my face? Okay. Okay. So I explained why it was such a big deal. I was never supposed to be able to walk on aid again, and I was never supposed to be able to work a full-time job. So I was extraordinarily grateful. Vic was the type of advisor that thankfully didn't drop me like a hot potato because I wasn't exactly producing much research when I was sitting there on fentanyl drooling on myself. And I, just the last bit on that, when I was trying to review for the first round of exams, I sat in on one of Ty's groundwater classes and couldn't pass the test. So I'm very fortunate, and the past has been very good. And Luke, can you try to put that down? There's not that thing behind you. Thank you. Okay. And that brings us to the sunglasses. I'm not a piano player. I've had a migraine for 10 years. His name is George. And he's why I wear these. And some of my coworkers don't even know what color eyes I have, and that's just kind of weird. But at least I can keep working. Okay,
Better for you, Sean?
that is so much better. Thank you.
Well,
And so get tired of this slide. So we have 9 papers here. First, we'll talk a bit about the Mars work. I asked Vic if part of the challenge here was trying to discuss 9 papers in an hour. And he's kind of like, yeah, have fun with that. I'll just give I'll pretty much just show you the pages of some of the Mars papers, and I'll go into detail on one of them that is, I think, the most interesting. That's my favorite. And then we will talk about Forest Service stuff. The analysis of burnt watersheds. It's a big deal, becoming an even bigger deal all the time. And one of the big problems we have is we don't do it very well. The tools we have aren't very well suited for the problem. And then the final 3 papers. Oh, thank you. You are all lucky. She brought me the clock I asked for. Everyone here knows that talking is not a problem. It's the stopping. And then 3 papers on dealing with land management challenges under climate change. Everything from salamander to forestry. Well, that's interesting. So hopefully everyone hopefully everyone recognizes this planet. If not, let's talk later. This one, that's Mars. It's about 40% the size of the Earth. I have a bunch of constants up here and everything. Don't worry about them. That's in case they start asking me for them at the end. But it's basically just 40% the size of Earth, which means it cooled down faster and all these other things like that. And sorry, no canals. The first telescopes were very, very primitive, and they were imperfections in the lens. A lot of great science fiction came out of that. So this is one of the big features. I'd be remiss if I didn't mention it. It's called Weimar Mars. And so again, 40% the size of Earth, and that's its size. That's where the United States would be. It's huge. It's 10 times deeper than the Grand Canyon. And as far as where it is on the planet, this is our basic Viking imagery from the first things we sent there, and kind of can't see much. It's there. So we usually look at this. There is a Mars Orbital Laser Altimeter on a spacecraft that I love. It's called the Mars 2001 Odyssey. They had to do it, and they did. And so it got, essentially it's just LiDAR from space. And we did a paper on where it came from. Nobody knows for sure yet. It's an ongoing argument. You have everything from tectonics to volcanism to evacuation of water to, and this paper just said, hey, look, here's some extra volcanoes here. So you can't dismiss the volcano story. Good scientific mosh pit. This is the other big feature that everybody hears about, is Olympus Mons, or Mount Olympus, and it is very big. 95,000 feet tall. Everest is 29 and change. So Mars is a pretty neat planet. And again, there's our reference. Yeah, you may have been there once or twice. So back to our, I think they're getting like views up my nostrils. So that's where Olympus Mons is. And this big round thing, that is known as the Tharsis superplume. It covers 28% of the planet. It's the same, let me be careful. It's plume volcanism like we know and love on a ridiculously massive scale. It's very, very cool. And so this whole area here, that's Tharsis, and it formed, in one of the earlier periods, about 2.5 billion years ago. And here's a paper that we did looking at what was in place beforehand. It's just this little rise down here, and it would be a really cool place to land a spacecraft because it has like some bits that have a remnant magnetic field, because Mars used to have a magnetic field before its core cooled, and lots of neat features. And here's the paper I'm going to talk about a little bit. GRS, that was a gamma ray spectrometer. And the basic idea is that all elements, I'm not even going to go into spectroscopy. It's magic. And just like you can look at substances and in labs, figure out what they are, you can do it from space. If you want to talk about the magic, let's have office hours. So the big thing about this paper is this idea of paleooceans. Mars is dry today, for the most part, lots of ice. But at various points, a couple billion years ago, there were probably oceans on the northern plains. I tend to call them Oceanus Borealis because everything's Latin on Mars. And so these rough topographic outlines here are two potential shorelines that picked out based upon topographic features and all. And so what the shoreline 1 and creatively named shoreline 2. And so what this spacecraft did is it made elemental abundant maps from space. So this is potassium. And so you can look at the areas that are enriched in potassium and start making interpretations. This paper also looked at thorium and iron. And the basic approach is if shoreline 1 is here and shoreline 2 is here, just look at these isotopic, or look at these spectrographic concentrations above and below the shoreline. Just compare them. And same thing for shoreline 2, and same thing for a transition zone. So if these really were shorelines, they'll show up. The elemental abundances will show up in different places. It's a really neat paper, and I wish I had time to tell you all about it. But I did send a link to it along with all the other papers that have been published as part of the invitation. Another paper we did on Mars, I'm not going to tell you anything about except it exists, and that there are a lot of environments which probably paralleled early environments on the Earth. And so if life developed, those were the niches where it would have a good chance of still hanging out. So, and there's a lot of them. Okay, and then finally, the last thing with Mars is this crater here called Layton Crater. And it's a bit of a sore spot for me because we went and found a bunch of data, a bunch of images, a bunch of clays that they saw from orbit, and I went and did a paper on it for AGU 2009. And I applied and I got the crater named. There's ridiculously complicated criteria for naming different features on different planets. I proposed a name with it being under 60 kilometers. They found a spot where it was over 60 kilometers and chose a different name. But aside from that, I presented this at AGU 2009, and a lot of people were kind of looking at the poster going, oh, wow, this is kind of neat. What are you going to do with this? And I'm like, I don't know. And then I went and put in an application to NASA. I'm just like, we need boots on the ground. Geology, right? That's how you do it. Like, I will happily take a one-way trip. No problem. And they said no. Some nonsense about ethics. Yeah, right. I'm just like, with a vision like that, screw you, NASA. I'm joining the Forest Service. So, yep.
Good thing you didn't have couplings on those.
Yes, actually it is, because I was going to sort of like loosen them while I was talking.
So much for planetary science.
Well, I mean, kind of all the funding is tossed on the floor too, right? And just because I respect you all, put a tie on. This is probably one of a handful of occasions which you'll actually see a Forest Service person in a tie.
But this is formal.
What was that?
This is formal.
Yeah. All right. So, the other thing that, and yes, the papers started coming out about my little crater. And yes, one of them was in Nature. And I'll just leave it there. No, not so nice. I knew I was going to get scooped when I joined the agency, so I did. But, they don't get to play with a bear.
International Space Station Flight Control Room. We have a special visitor today. Seen in this view is Smokey the Bear mascot next to astronaut Mike Fossum.
Yeah, NASA doesn't get to play with a bear. And there he is on the space station. So, next line of defense, NASA doesn't get to play with things like that. So, this was the Dixie Fire on my forest, summer 2021. And it was the largest single wildfire in California history, just under 1 million acres. I apologize to the professors for imperial units. Don't start twitching. Now, to be clear, I am not a firefighter. I don't play with these things. That's as close as I get. This was the night before that, And I was racing up to some springs to get out my data loggers in case the fire went that way. You know, we shout out to Shannon Prather and all of our firefighters, some of whom may be sitting down watching this. You know, they're the ones that do that dangerous work. When it's safe, I go in and do something called bear work, burned area emergency response. I'm a writing nerd, so I cannot tell you how many times I've twitched about it being burned and not burnt. Curiously enough, people are not that interested, in my opinion. Yeah, no telling for taste. So this is the paper that I was talking about that Kendra Fallon and I did last year. She's the regional fire ecologist in California. And basically the idea here is everybody's like, fire. We need to model it. We need to figure things out. You know, just everybody mob the scene and do the best you can. And a lot of the time that's helpful. And a lot of the time, not quite so much if people start doing things without the information they need. Like for instance, this is known as soil burn severity. When you model a wildfire for watershed purposes, you care about the soil. Now, what most people use is that, vegetation burn severity. Now, these are both on the same 4 scale, low or unburnt, low, moderate, high. So, like for instance, a third of one of the major water supply watersheds in California, Lake Oroville, third of that burnt. And a lot of people are modeling it. And a lot of people are using this. I was at a conference and, I kept having to ask the person next to me, like, am I being a jerk in my comments? Am I going to get thrown out here? Because, look at the difference. And models are inexact enough as it is. And so that's the point of this paper, was to move this knowledge out of bear and hopefully into the wider fire modeling community. We'll see. And then Kendra and I had so much fun. We started on another paper. This one's not finished yet. It's 100 pages so far. Yeah, it's not going to go to a journal. It's going to be an agency document at this point. But the basic idea is, we've all heard and seen that, right? Hopefully. Well, that's the rest of it. And, it's everybody sort of pauses, like, oh, that's revered wisdom. Yeah. And then forgets it. Einstein said, model, he's talking about theoretical physics, but it applies to models. Things should be as simple as possible. In physics, they talk a lot about assuming a spherical cow. And depending on what you're doing, that might be an okay approximation. One of the other things in modeling, though, that's an isocohedron, also known to gamers as a 20-sided die. And if you tried to model a cow as one of those, not so good. There's no reason to justify the additional complexity. And in the additional complexity, you have to make it meaningful, and it's just a mess. And so one of the big points of that paper is, look, anything you do, you need to ask these 2 questions: how wrong and how useful. The phrase needs to stop being a platitude. The rest of the quote from Einstein: as simple as possible, but no simpler, right? Meet my friends, the curve number method, and the universal soil loss equation. Both over 50 years old, both made by the NRCS, both of which the NRCS now says are used when it's not strictly scientifically justifiable, such as they're made for that. You know, this is Illinois farmland. And in bear work, we use them on that. And we use them on that. And these are pictures I took in 2017 from a helicopter. We were trying to assess this fire, see how bad everything burned. You know, all of these, that was all covered in conifers. So it wasn't like a rocky highland on its own. And stuff like that behaves very, very, very differently than stuff like this hydrologically. And yet, that's what we're doing. Part of the reason why is we don't have anything better, and by statute, we have to do something. And that's one of the big problems with a lot of the environmental laws from the 70s, is they made a lot of things required that sound like really good ideas. You want to know the cumulative watershed effect. But if you can't scientifically justify what you're putting together, that's a problem. So this is a warning from this gentleman. He was the chief scientist in New Zealand in 2014, and this is one of his 10 rules for his job. Recognize the limits of science. Science can increasingly address complex questions over which policymakers and elected officials agonize. But scientists must not overstate what is or can be known, even though the shift from a view of science as a source of certainty to a source of probability can frustrate and confuse decision makers and the public. True story. I just went round and round with the EPA. They wanted these numbers for change in the amount of sedimentation from roads, and I'm like, you can't quantify that. You know, the changes are you know, anything you want me to quantify is meaningless. It's deceiving. They're like, well, we still need a number. I'm like, can I give you a paragraph about uncertainty instead? Doesn't go well. So within the context of bear, one of the things I did in this paper is I'm like, let's step away from these numbers with no uncertainty statements. Let's step away from giving them exact numbers with decimal points and all this. You know, give them the number, that's fine. But I was proposing a questionnaire like this to go with each report. Essentially, you know, the quality of the approximation, how wrong is it? You know, and all these things that go into models, quality of the data, the calibration, on and on. And then to sum it up, a model's total confidence level in the product, so people know how useful it is. So we'll see. This is going to go up to the national bear leaders at some point here. So see if I still have a job next week. Okay, so now we're just going to move into these land management, straight land management problems. That's Mount Lassen. Last erupted significantly in 1917. When I recruit people, I always say, come work in a geologic playground. So the first of these three papers is, I don't know why we do these names. Impacts of climate change on groundwater availability on spring flows, observations from the highly productive Medicine Lakes Fall River Highlands aquifer system. Do you have any breath left at the end of that? I don't have time to really go into this, but I need to make this point. So, you know, this is just fractured basalt and it behaves like pseudokarst. You see a lot of these sort of modeling studies for these Snake River flood basalts, for instance, and similar terrain. So this is Burney Creek, and about a mile downstream, you have this, Burney Falls. That's pseudokarst. It's not limestone, but if you saw that in Arkansas or Indiana, you'd still be impressed. So a lot of the management problems we have are also because people don't understand groundwater like this. And yeah, it's like, no, you can't put in a monitoring well and monitor your whole forestry treatment. It just doesn't work like that. And the just to give you an idea, this Shasta Lake Reservoir here that flows into. So this is back to the Fall River and aquifer system. So we're talking 6,000 to 10,000 gallons a second coming out of this aquifer. 17% of the inflow to Lake Shasta, so it produces 5% of the state's hydropower. And this is just this little volcanic cracked aquifer up in the corner that no one pays attention to. It's an interesting study. Again, it's linked in the announcement. We looked at it under 4 different climate change scenarios. And, unsurprisingly, it was just not good. Recharge goes down, discharge goes down. Right, and then one of the 4 scenarios had more recharge just because all of the snow turned wet. Next, salamanders, because what goes with ancient Martian magma like salamanders? These are another losers in climate change. These guys. This is the whole reason I had to include salamanders is just for the picture. It's like that just like erase a host of bronze. This study was basically saying, can we thin around their ponds because they're so overstocked? The trees are going to get diseased and die. The trees are going to burn down. But these were recently designated Forest Service sensitive, and so that means they don't have a bright future. And so we're like, hey, can we thin around their ponds? And they were okay in this study. Hopefully, we're going to do a follow-up, longer time period. Hopefully, they're okay then too, because we don't thin, good chances it'll just burn down. And that's even worse. And that's a scary thing that we're actually at that state of things when we're having to start thinking. And the final paper, and I'm going to talk about this one. So, again, ridiculous title: Soil moisture and micrometeorological differences across referenced and thin stands during extremes of precipitation southern Cascade Range. So the whole summary stuffed in one statement. The basic idea with this one is we got a big chunk of money. It's called the CFLR program, and it had monitoring requirements with it. And so I started jumping up and down, and my boss is like, okay, we need hydrologic modeling. Here's a chunk of money. What can you do for $200,000? So I got with Scott Tyler, University of Nevada, Reno, and Gordon Grant, and we put this project together. So basically, we had these stands that had just been thinned, quite literally the year before. The timing was amazing. And in each of these figures, you have just sort of our basic conceptual model. what our guess is. And, so our thinning prescription, it's not taking any particular point down far. It's just sort of bringing everything down. And then we had a seed cut prescription, which is basically when you make a clearing, 1 to 2 hectares, and you leave the biggest, strongest trees in it to be seed sources. Because if you can avoid planting, good. Because planting, it introduces other genetics, it's expensive, it doesn't work as well, blah, blah, blah. We're trying to get these systems so they can manage themselves rather than needing us. So, and then we had a control. And so what we did, this is in the seed cut. We put micromet towers and buckets and solar panels and computers. We put out, since it was Scott Tyler, so this is one of the fiber optic lines that was mentioned in the Darcy lecture. And just instrumented the whole hydrologic system. And the point of it was supposed to be focus on snow. Because that was the biggest question. It's like, okay, how can we do forestry differently to retain more snow? Because snow is a lot more effective than rain. So, soil moisture meters, of course, all that's fun. Takes a very long time to get all that sort of dirt out. So what I'm going to show you now, the way I put it together is the slides bounce from left to right. So that way you're able to see the previous slide that I just showed to compare. So like this is the 1 meter LiDAR bare earth model of the site. And this here was our unit. Okay, everybody see how it just moves to the other side? So before we treated it, it looked like that. That is in 2010. And so those spots are where the seed cuts are going to be. The green hatch there is our control. And the rest of that unit got that diversity thinning. And that's what it looked like post-treatment. And so here's that unit put back with contours. So one of the things we look for in this site is fairly uniform physiography. You never find a nice, beautiful engineered slope out in the woods, thankfully. Those are kind of the best we could do with that. And this is our fiber optic line over here, about 1 kilometer long. And those were our micromet towers. And so here's our design. Just your basic hydrologic cycle monitoring. And so we did a successful proof of concept 2012. Great, wonderful. We got a full deployment. We put it all together, and then we're like, wouldn't it be funny if it stopped snowing? And it's like, yeah, we're scientists, we're not superstitious, but don't say that. And we all know what happened next. This is the drought monitor indices for Shasta County. And our study was right there. So, yeah. For those not familiar with these are drought ratings. So the darkest colors are the worst droughts. Yeah, exceptional drought. And there's our study. Beautiful. As I said, just hilarious. So it actually ended up being kind of interesting. So this is tree ring data. the chronology at the site, we got it back the early 1900s, and the rest of it's available in paper. But this is what we're looking at. And, well, 2011 here when we thinned. And then about 2013, things took off. The ones that grew the most were the seed tree treatment. This is superimposed, again, that's our study period, with those droughts, which is kind of interesting. We got this much growth, even with that kind of drought. So we started getting a little excited. So that is our exceptional drought. And 2017 was extremely wet in California. And then we got an average year. And so this ended up becoming this data set where we had it through extremes of precipitation, which was really cool and completely not what we had planned. We were going to look at snow. Yeah. And this is a niche project. You already know the answer to that. Forests all over the West are changing, transitioning. They're out of equilibrium. It's a huge management problem. All these areas have been snow-dominated winters, where all the animals, the plants, everything are adapted to that, are now rain-dominated. There's your occasional patches of snow. That's a big deal. Those who aren't hydrologists, it's your snow that is your water supply for the next year. And it's your snow that moderates a lot of the events. Just said that. And aren't allowed. And so this area, it's one of those designs where we had to exchange replication for length because we only had so much money. So we were really careful on how broadly we're going to apply it. But it's certainly representative of Southern Cascades, Northern Sierras. And that was our original design, and that's why they call it research, right? We added, dendrochronology, sap flow. We sucked water out of the roots and did isotopic fractionation. And the entire thing isn't done yet. The snow story, such as it was, isn't in the paper because, we had enough snow to turn on the fiber optic lines a few times. We have some photo points, and there's work to do. And then the root water data needs to get out as well, but that's for the future. So that was our original design, and then we added our sap flow trees, added, they were called Brown's transects, just cataloging of all the debris of the understory, all the standing fuels. And we still got to do some science. So there's a lot here. I'm just going to pull out some highlights. We're really interested in soil moisture decline for obvious. If you're a fire guy, they're obvious. As soon as the soil gets dry, things dry out and burn easier. So again, because of lack of replication, we were trying to be very careful with how broadly we interpret it. And soil moisture curves, as I understand them anyway, are more stable at the ends. So, thank you, Forest Service IT. Oh, that was interesting.
What are the green, red, and yellow? What are they represent? I can't read that. Midley side.
You're kidding? I can't read it from here. So the green is the control, the brown is the thinned, and the orange is the seed cap. Yeah, and I don't know what this computer just did. I'm seeing something entirely different. Oh, that's cute. No, I see nothing. Yes, I have a smart phone. U.S. Forest Service IT is very special. I don't remember U of A IT being a walk in the park, but they have nothing on the Forest Service. So you're still. Oh, it opened the paper. Cute. Okay. Are we? We're not. Okay. So we specifically looked at, the initiation time, the rate that it dropped, and then the final value when we were doing our evaluations for the season and what we were interested in. And what we found, both thinning prescriptions had a modest and predictable impact on below canopy micrometeorology. So, in other words, forestry works. Yay. If this didn't happen, we'd know something was really wrong. This included the lower nighttime minimum. Forest insulate. Let me break. So when do I need to end? Because we started really late. I'm sitting here looking at the time.
Started a little after 3:30.
Yeah.
Yeah, well, typically in these exams, there's a public part, which you're doing.
Mhm.
And so we could have some public audience questions and discussion, and then we'll go into a committee part. So we're at about that transition point. We started about half an hour late,
Right.
and you've used a little more than a half hour. But let's call it half hour with various technical things. So you're fine, but obviously the committee.
I'll throw in my 2 cents, which is just that I remember Ty saying he was only free until 5. So we just want to make sure that we reserve some time.
Yeah, we want to have time for the committee. So it might be well to take some of the general audience questions and then go into the committee session.
Yeah, Sean, you can wrap up.
Yeah.
Relatively short order.
Yeah, I have a series of conclusion slides, and I'll just grab the most important ones. Not those. Oh, this is. So the onset of soil moisture decline is governed by precipitation as well as density. That's a really important result. I'll tell you why in a moment. Okay, well, this is one of the other big results. Is the everybody's expecting like a linear response. You cut more trees, you get a correspondingly additional amount of water, with some wobble here and there. We were really surprised about this. So the 15% of control, that's our diversity thing. And that largely had the same impact as reducing it to the seed cut. The end of soil moisture. So,
Are we seeing the same thing you're seeing?
wow. No, we're not. That's really special. Sure. Why not? Stop share. Okay. So that explains the faces. So I was like looking, I'm like, okay, something's clearly not sticking. No, it's not. We always use Microsoft Teams at work, so I don't know where anything is. Of course, they use Teams. They really know where everything is on that either. Hooray!
Okay,
Okay. Oh, okay. So that's what I was just saying is the fact that the magnitude and the changes between what we got with 2 treatments was really surprising to us. And so that is the kind of odd suggestion of that. Some of the tree people we talked to weren't surprised. Some were. That, that is something that needs to be tested further. Let's see. And let's have this be the other big point here. So again, thinned and control stands, the amount of soil moisture at the end of summer in the other upper 100 centimeters was very similar. And whereas in the seed cut, taking those extra 15% of trees, you have a lot more moisture. And I'm thinking I should just give you the broad picture instead of going through. The basic results from all this that's interesting is everybody's like, well, we need more water. Let's cut trees. Yay. And then you have people with the state going, we want water in the streams. Can we pay you to cut streams? And then I'm over there in the chair squirming. The original reason we got the money to do this is because they wanted to find out if they could cut water or cut trees and get water in the streams. What happens is you get a flush of water for a couple of years, and then it gets reallocated in the system. That's why you saw the tree rings get bigger. The trees are like about a year or two, and then their roots figure out, ooh, there's something here worth doing. These areas were planted also, and those took about 4 or 5 years to really pick up the water. So you see stuff like that, and one of the big things in these systems is when the trees turn on, when they start using the water, because they turn on earlier in the control where it's warmer. Because having a stand of trees insulates things, right? So things start growing first. Nod. Okay, just checking. And in years where precipitation is limited, those trees used up the water supply and then it wasn't replenished. So they were in terrible condition late season. But in years that were not water limited, they started using the water and then it would be replenished again and again and again, and they'd be better off. So that's why the magnitude of the soil moisture at the end. That's why that first conclusion was saying, well, it depends on the season, depends on how much tree silt we get. That's one of the big findings, and the other big finding, and I'll stop on this one, is what we're calling seed cuts. These areas, they keep yes, get rid of all those trees, and yes, in theory, you have a lot more water, but something's happening. And in theory, you get a lot more water, but the roots can't take advantage of that water. It takes quite a while for them to be able to. You also have the effect of the bigger openings, the more wind, the more desiccation playing off against it. And then, and then the other factor is everything we do, we try to turn back to fire safety in some way or another. And the bigger an opening, the more, the drier the surface fuels will get. And the drier fuels you have, the easier they light and the easier they'll carry fire. So it's all these different factors working off against each other. I was going, ooh, unknown error. We've been having those this entire.
I think it stopped, if you look there, it stopped projecting
Oh,
just a minute ago, so.
well, that's fine. Well, actually, no. So well, I completely ran off. So I'm not going to be able to show you my conclusion slide, which is very sad. So what I was saying, so it's those results suggest that these 1 to 2 hectare openings are too big. That are optimal size openings are probably maybe like half hectare or something. And that was one of the slides. And the slide I really wanted to show you, that's my conclusion slide, but it's Zoom crashed altogether, so you're not going to see it.
Just tell them.
Wow, it's one of those things you have to see. You know me enough, Vic, to know I'm a visual guy. Well, computer's talking back to me. Yeah, forget. So the big point was it was one of those smoky, old school smoky pictures. And so the big joke is like, yeah, well, you keep doing research in these things and you find interesting things. Well, the rest of the picture has Marvin the Martian there blasting. So that was my wonderfully planned tie together. So there you go. And please rest assured it would have been fun.
Hey, let's take some questions from the audience before we go into the committee session.
How do we do that?
So, do you have a question? Unmute and just go ahead.
Oh, well, that's easy.
No, it's really hard to read. Lots of previous steps. I'm really interested in the Mars part. And I want to know how long the Marshall patients give you ocean. How long is it a long time process or is like like short time and how different from
I would-
You might
So
want to repeat
the question, so because I don't think the online
Okay.
audience can hear. Just repeat
So,
what the question is.
The question was something I really would like to know as well. She asked, so these Oceanus borealis on Mars, if it in fact did exist, how long lived were the features? And I would love to know that too. I think it's an excellent question. One of the things about the spectrometer study is that it, all the evidence it was showing, isotopic evidence for the oceans, a lot of it could have been explained by volcanic processes. Really the strength of the conclusion there was all the different lines of evidence sticking together. But as far as how long lived, I've seen theories from very long to just very short interspersed. And so, yeah, please.
Yeah, sorry.
But you also have another question I can't answer?
Yeah, a lot
right.
of questions, a lot of interesting points, but so I will just move on.
Yeah, please.
And I like your paper about hydrological analysis for that. And you have a table assessment of simulation or modeling of
Mhm.
and do you have an example to build those lines? Like
Yeah,
how useful and how wrong it is?
Remember, repeat the question.
yeah, thank you. So the question was, when I talked about the meaningful modeling paper for post-fire hydrologic analysis, sort of the qualitative questionnaire to evaluate the modeling job. He asked if I had had a example of that filled out. And I don't, but I probably should. In the paper, it both for runoff modeling and soil erosion modeling, it traces 2 fires. One of them was the Eclipse Complex, which I showed a couple pictures of, and the other was Bulb Fire, which was much mellower, not many values at risk. And so we track both of those through the paper. So that's a good idea. I probably should work that out for both of them, as an example. Yeah. Anything else?
So anyone from online,
No.
see if anyone online wants to unmute and ask your question.
Vic is saying, anybody? Okay, there's nothing in the chat. Anybody want to unmute with questions? Anybody trying to and can't? Could you say that in the chat? Okay.
I have a, you go ahead.
On the Dixie fire,
Yeah.
you showed the difference between the the soil burn severity, the vegetation burn severity.
Mhm.
Have you, just in your own observations, how has recovery progressed in those 2 categories? Do you see soil recovery happening at the similar rate of vegetation recovery, or does one persist longer? What are you seeing?
And again, repeat the question, please.
So the question was about the Dixie fire and looking at areas that are moderate versus high soil burn severity. And it is a major difference. I mean, in general, the rule of thumb for fire used to be, fire bad, and now we're like low intensity fire good, very, very good, high intensity fire bad. And that kind of translates to soils as well. Your high intensity burn soils. I mean, the pictures I showed you on those bluffs, some of it was white. And when soil gets burnt that much, it loses all its structure and it just sits there like flour. And that stuff, I mean, there's usually nothing to hold it down because all the needles are burnt, even all the stumps have been consumed. And so first winter, yeah, I mean, stuff like that, I mean, 100 years, you're still not going to get it.
One of the questions I came up with when I was reading about your the seed cut versus the control and so on, is that you noticed that the seed cut ended up having a higher soil moisture content afterward, soil moisture storage. But you even said in your presentation that the trees that remained thrived really well because they used up all that extra water, right?
Well, they couldn't take advantage of it
But they couldn't, but in subsequent seasons.
Eventually their roots figured out that
So
there
is
was
that
stuff going
advantageous then? Is that what you would want? I mean,
on.
that gets a little tricky. And the other question I had is there were discussions about this for the San Pedro, which is of course different ecosystem, but it's a protected riparian area, and people said, oh well, if we need water for the river, let's just cut down all the trees. Yeah.
No.
Right. But I think there's different studies that have shown that if you cut the trees down, it does indeed have a rebound effect on the water, but it also risks invasive species coming in and taking root, like tamarisk, salt cedar. Have you seen, I mean, it was only fairly recent that you guys did this experiment. Have you seen any evidence of other invasive species or maybe risk of invasion from like bark beetles or something similar?
Yeah. So on that site, we planted it with new ponderosa pine, And part of that process is you go and you get rid of weeds and stuff like that. So, I mean, there was active management of weeds in that site. But generally speaking, yes, you can get problems with invasives. It's like everybody gets excited about that idea, but it's just like all natural systems are equilibria. And the more you pull something out of equilibrium, the more extreme the results are going to be. And so, and you have to cut a lot of trees to get a result. But the bigger thing is it gets reallocated in the system. So you have to keep other vegetation from growing, which in a healthy ecosystem, you're going to get that by regular low intensity fire. Or in a land management agency, hopefully we'll be doing prescribed fire frequently enough to keep it down. But yeah, I mean, I've had so many arguments with people in the public and in the agency and everywhere. It's like, yes, I know the spring started flowing after you cut the trees. Go back 5 years later. Yeah.
Okay, well, I think we need to allow some time for the committee. And so we thank the audience. And I think those who aren't members of the committee, and for online, that's just Ty, who's member of the committee. So everyone, hope you enjoyed it, and go off and have a nice day. Yeah. And you can sit down if you like for the rest of this.
Thanks for inviting me.
Yeah, it's good to see you, Phil.
Oh, yeah, good. Yeah, yeah, good seeing you again. Okay, so you got lots of messages, Sean. You got lots of messages from departing folks. We had a whole team of contacts. Yeah.
How many times in your life do you get a chance to like assemble practically everyone you know to show them something cool?
Well, I'm making lots of contacts.
Good showing.
Yeah, I'm delighted. I wonder if it'll. Oh, I'm not a member. Yeah, it booted me out. So I wonder how did it. So it's still recording.
Okay.
Okay.
That's well, you'll have the recording because you said that that won't be on my laptop.
We'll need to stop the recording though and switch out the room.
Yeah. Yeah, so you'll have to turn it off at the end when we deliberate.
Wow, a lot of people there.
And unless you want to record all of our questions, sure about that. Up to you.
Oh, might as well.
Yeah. Well, you don't have to keep it on for questions, but we need to lose the audience.
Everyone online needs to go off except for Ty.
Yep. So have a good day.
Thanks for coming. Bye-bye. Thanks for not throwing anything.
Well, it's pretty hard when you're online.
There are tomato icons.
Yeah.
It's my mom.
Yeah. Yeah. Okay. Maybe some people are.
Oh.
No, they're
good.
still going. Okay. Yeah.
Okay.
Yeah, we have to have everybody.
I need you to get heading off, Tyler. Thanks for coming. Oh, and well, our archaeologists are hanging around.
Okay.
And Bob?
Robert. Maybe Robert's asleep.
I think you might be able to like miss someone.
Let's see.
Yeah.
Show selfie. Yeah. What does the button do?
Well, you should be able to pull down the names. The host can dismiss people, I think.
Yeah.
Like if you go to.
He probably just left the room.
Yeah.
Left his computer on.
Hide non-video.
I have no idea, and I can barely see the thing.
Uh-huh. Well, let's see here if we can get something. Okay, well, wait a minute. I'm losing power on the computer because it wasn't plugged in.
I had, watched your video today.
Oh, good.
And he was really, and, learned a lot from your interview.
Yeah, that was fun.
Yeah, he was excited to learn about it, and, yeah, very good. So anyway, you're making a difference, left and right.
Cool. Well, maybe.
Yeah, I think next thing what I'm gonna do is I'm gonna require you to, check for professionals on LinkedIn, on LinkedIn.
Not nominally. I have a stable job I love.
Oh, yeah, but you can still post things about what you're doing in your job and.
So we need to have the online people leave the meeting?
Robert Patterson and Robert Goldman need to leave.
Yeah. So we still have Ty, but
Is there a way to,
Why don't we just close it?
let's see.
that's one way.
Yeah.
This is,
That's what you get when you do that.
yep. So we're not getting much volume for Ty.
Button chat. Oh, that is the chat, isn't it?
Yeah, that's the chat. I don't need that. How do we get rid of people? Okay,
One more.
Robert.
Dolman, gotta go.
yeah, he's got to turn off. I do that.
What happens if you click on those
Yeah,
three dots?
not
Try
that
that.
one.
I've tried that. Hide non-video participants. Hide them? And we want to delete them.
Are you the host?
I assume so.
You were the one who started the meeting, yeah.
I started.
Could you get Bob to disconnect? Yeah, he's logged in here. And
We have to have a private meeting.
Go ahead and stop recording.
Yeah, stop recording.
That's you.
You're on. I'm not. I think that's on.
I'm not even hooked up anymore.
Okay. Well, is this where's recording?
I told it to automatically record to the cloud.
Yeah, I don't think I have
Yeah,
anything on mine.
Still saying.
Yeah, it's still saying record. Okay, Ty says we can close the meeting and restart.
Yep.
Shall we try that?
Yeah. Okay, good.
Okay. We'll do that, Ty. We'll leave, everyone will leave meeting and then we'll restart again with that meeting code. Okay, I'm closing the meeting.